So in order for me to show you that, I'm going to show it to you with a code, and the example I'm going to give you is a review of something you have seen, which is a universal shift register. So the register we constructed when we talked about D flip-flop is just a register that can store a value, but generally speaking there are shift registers like that translate parallel to series. There's a bunch of other register. So the one I'm going to be talking about is what we call a universal shift register. So this particular universal shift register does the following. It can either remain in the same state, basically nothing happens, or it might shift its contents to the left. Basically it can do a left shift, or it can do a right shift, or also it can load a parallel data. Basically if it's an 8-bit universal shift register, it will load these 8-bit. And why do we need universal shift registers? Universal shift registers, they're called universal, they're very versatile. One way to do it is basically one of its application is to load something in parallel. Let's assume that you have some sort of an 8-bit or 16-bit data. You can load them in parallel, and then you can start shifting to the right one at a time, or shifting to the left one at a time, or the right, doesn't matter. And basically you're using it as a parallel to series. Okay, so you load in parallel but you output it in series 1 bit at a time. This is very common when we're talking about some sort of a communication systems, and we're going to see it later. For example, I have a register in here, I have a register in here, and in order for me to avoid connecting them by 8 wires, I can connect them with a single wire, and then I can load these with 8 bits in here. For example, I can load that data bit in here, and I'll have all 8 bits, and then I'll send them over the wire one at a time. And the other one here, which is also a universal shift register, is actually shifting. For example, if this is shifting to the right, this is also shifting to the right. Okay, and you're loading them 1 bit at a time, and after 8 you can actually read out these 8 bits that you actually inputted. And this way it's one use of a universal shift register is if you have a couple of them. So you do a parallel to series in here to send that, and then you do a series to parallel to get that. So you transfer the data from one point in the system to the other point of the system using only one wire, because for some reason or another you can't have more than one wire. We're going to see it when we talk about communication protocols, but for now what I want to do is I just want to implement this particular system in here. So how do we implement it? Well, this particular block should actually help us. So you're going to see here is I have exactly 3 parts. So I have a part in here, and that's basically the combinational circuit that actually specify my next logic. I have another one here which actually specify the register. Okay, that's the state of the system, and technically the output in here is just as simple as the status of the register. There's no circuit or anything. So you're going to see that in the code I will be basically coding these 3 separately. And it's as simple here, the example here, I'm not going through the design of it, but it's as simple as implementing it as a multiplexer. So the multiplexer can take, for example, if you want to remain in the same system, the remaining state, basically take the output and put it as the input and select that. So the control signal will tell me what's happening, actually what's my next state is. The other 2, we're going to see that they're simply, basically, we're going to take the D, which is a new data point, a new input. We're going to take the least significant bit or the most significant bit, depending on what, and we're going to put it in these wires and select it. And the last one, if I want to load a completely new parallel data set. Okay, so what do I get out of here is I have a whole system. Let me just do that in here. So I have a whole system, and you can see that that system does the following. So technically it has these types of inputs and outputs. So it has a Q as an output, it has a D as an input, and that's basically a bunch of bits, an N number of bits, and you have control, which is 2 bits. And of course you're going to have a clock that should be exposed to the outside world. So the way I did it, basically I just wanted to see what are my inputs, what are my outputs, and I was able to see that I have 3 types of inputs and 1 output in here. So let's go to Vivado and implement it. Okay, so in Vivado we're gonna have to go in here and create a new source file, and that new source file we're gonna call it, for example, it's actually a system Verilux source file. We will call it let's call it universal shift register, shift register. Okay, and it's gonna be an SV. We're gonna do this and finish, and of course it's gonna tell us, you can of course fill it out here, but I'm just gonna type it. Alright, so we're gonna do this. I'm gonna make it my top file. So okay, So this is how it is, and we can simply just basically, I'm gonna just tell you that I'm gonna use a parameter, and I'm gonna call it n equals 8 for the number of bits, just to make it more generic, more scalable. Okay, and I'll just basically put a tab in here, and I'll say, okay, so what type of input we had? We had input logic. Of course, we have the clock, we have the reset. Well, I didn't show you the reset in the diagram, but hey, we can put a reset, and we do have an input logic, and that's basically the control, and it was 2 bits because I have 4 types of functionalities that this particular universal shift register does. And of course, we have the input logic, and we called it D, and it's actually an n-1 to 0 D, and that's basically the input, the data point, whether I'm loading an an n bit data point, or I can use the most significant bit and the least significant bit for the serial shift in, as you can see, or as you will see shortly. And then we can do the output logic, and this particular output logic, for example, it's the same, it's n-1, 0, and Q, and that's pretty much it. So we have our inputs and outputs. Now we get the functionality. So these are the 3 parts, and what I want you to see is there are actually some internal signals which we call R next and R register. So I'm going to just define them. They're just easier to deal with this way, and this is actually very common when we deal with the sequential circuits. So we're going to see signal declaration, and this here I'm going to call it, it's actually type logic, and of course it should be the same size as of the input and the output of the register, so it has to be of the same size of the register. I'm gonna call it R next, and R reg is actually, as if you can call it, you can basically figure out the input is the R next and the R reg is the current state. That's basically my D and Q for that particular register. But now it's easier because I know that next this is what's happening, and R reg is actually what's the current one is. Okay, what's the current value is. All right, so let's get started. So what I'm going to do is I'm going to call them 1, and I'm going to call it 2 because I have 3 parts. Remember, this is what the guideline is telling me. So I have 3 parts. So let's figure out what the first one is. So the first one, or we can code them, doesn't matter. Like the order at which we code them does not matter. Like we can name whichever one of them is 1. Remember, everything is parallel here in System Verilog. So for me, I'm gonna just basically say the 1 is going to be the register itself, which is the easiest of the 3 probably. Well, not necessarily the easiest. Probably the output is the easiest, but we're gonna see that it's actually register. All right. Well, it's a sequential circuit, so I'm going to use an always FF, okay? And then I'm gonna say at, and you don't have to use an always. You can use whatever system you have. You can instantiate a module here. You can use an always. You can use a continuous assignment. It's up to you. I just happen to be when dealing with synchronous circuits like registers and whatnot. It's easier just to use an always always FF and describe it behavioral. Okay, so we're going to do positive edge of the clock, and of course we're going to do the positive edge of the reset, okay, so that we have an asynchronous reset, and this is basically my begin and my end, and it's as simple as saying, okay, let's see, if it's reset, well, the R reg has to be set to 0 for the next time, okay, else what you need to do is the current value of the register has to be whatever we put at its input, which is the R next, okay, and that's as simple as it is. That's basically, I just put one of the 3, which is basically the one I highlighted in red. This is that part. Okay, what about part 2? Well, part 2, for example, or the second part, it could be the output or the input, it doesn't matter. So let's deal with the input, since it's actually what we call the next state logic segment, okay? Segment. Okay, so well, you can do it the way you want. For example, you can instantiate some sort of a 4x1 multiplexer, the one we built previously, and just use it. But what I'm going to do is I'm just going to describe it behaviorally using it always combinational. It's a combinational circuit, so you can always use always comb, not always FF. Okay, so that's good. All right, so what I'm going to do is since it's a multiplexer, I'm going to use it's a multiplexing. It's basically routing. It's multiplexing, so I'm going to just use a case. It's not a priority multiplexing network or priority routing network. Okay, it's a multiplexing routing network. So I'm going to just use a case. And I'm going to say, well, it's based on the value of control. I will be doing one of the following. I'm going to say end case. This is usually my style. Whenever I open something, I close it. It's just easier to track that way. So I'm going to put all the values I can actually get to bit 00 or to bit 01. or 2-bit 1 0 or 2-bit 1 1, and I usually like to do the default, even though I accounted for everything, but I will just do the default. Okay, for the 0 0, if you take a look at the graph, it's basically telling me that I just want to remain in the same state. So that means the next value should be the same as the current value. Okay, and that's as simple as it is, nothing else. And as you can see in here, in the upper one, in the always FF here, I use non-blocking assignment because this is actually a sequential part. And in this part here, which is part 2, I'm using an always comp, so all the assignments have to be blocking assignment, okay, because they're combinational circuit. Okay, that's good. So then we do our next in here. These are basically the serial in and serial out, and I'm just going to use a concatenation. It's just easier to write, and you can read it on your own. It's not really difficult. I'll explain it briefly, but you can see what I'm doing is here I'm concatenating. I will be using the least significant bit of D, which is an 8-bit, for example, or well, it's n-bit depending on how much we have. I will just basically stick it to the least significant bit, and then I'm gonna keep the n minus 1 or n minus 1 upper bits here. Okay, I was just basically concatenating them. And if you think about it, this is basically a shift to the left side. So I'm pushing everything to the left side. The same goes for the next one, which is basically a shift to the right, and you can see it's also using concatenation, and this time instead of using the least significant bit of D, I'm just going to use the most significant bit of D. Okay, and I'll keep the other bits in here, and of course I'm gonna have to drop the I'll have to drop bit number 0 from the RR reg. Okay, and that's basically it. Okay, so let me just do this here, write them in a comment so that you guys remember that this is a left shift and this is basically a right shift. Okay, so and then the last one is actually a parallel load. Is as simple as the D flip-flop we did before, which is R next equals just D, and that's basically it. So now I have everything I want. Of course, the default, you can skip it in here because I counted for everything, but usually what I do is I say, well, the R next equals R reg. Basically don't change anything. That's what I would do for a default case, just in case something happened like an error or something like that. All right, so the third part is basically output logic segment, okay? So the output logic segment, if you take a look at here, there's no logic. I'm just basically taking the odd register as is. So all you have to do is just assign the Q, because this is the output we see. We don't see the odd reg, we see Q. You just basically do a continuous assignment this time. I didn't have to do an always, and it's basically odd reg. And that's basically it. So if I actually go in here and say, all right, show me the schematic for this, I'm just going to load it in here and show me the schematic, and you should be able to see a universal shift register with everything we described as is. Okay.